We'll now introduce the two parent rational functions. We've actually looked at one of these, f of x equals 1 over x. We looked at this briefly in the earlier part of the course when we were looking at that library of functions, those basic parent function shapes that we could perform transformations on. So this one should be vaguely familiar, but we're going to study it in more depth now, and now we're going to introduce f of x equals 1 over x squared as well. So we're going to study these two parent shapes, and then you guys will be asked to do transformations on these. So you're now expanding that library of functions, those basic shapes that you guys know how to transform. So if you remember, the shape of this first one, the 1 over x, if we draw our two axes, so if we wanted to pick some easy key points, you know, we like to plug in -1, 0, and 1 for x if we can. So if I put in a -1 for x into this function, 1 over -1 will give me -1. So I'm going to have the key point, -1, -1. Now, if I plug in a 0, we can see that it will cause this function to be undefined. And actually, that causes what we call a vertical asymptote. I'm going to draw an imaginary boundary, dashed boundary line when x is 0. So on the line, x equals 0, which is our y-axis. So it's kind of hard to sketch it, you know, on your paper without colors or pencil and pen. So just kind of make that maybe just to the side of that axis so you guys can see that boundary line, that vertical asymptote. And then when we plug in an x value of +1, 1 over 1 will give us 1. So we'll have another key point over here, 1, 1. And those are some perfect points to choose because now the general shape, when you guys sketch the shape, you're going to have a piece in this bottom in the third quadrant, and you're going to have a piece up here in the first quadrant. So you're basically going to fit a boomerang-looking shape. Obviously that's not a formal math term, but some of my students have described these as the boomerang shapes. You're going to fit it in this third quadrant. So it's never going to cross. This is going to get closer and closer to this vertical asymptote, but never cross it because the graph's undefined there. And then in the first quadrant, same thing. You're going to fit this boomerang-looking shape in the first quadrant. Again, it's never going to cross this vertical asymptote because the graph is undefined there. Now, this function also has a horizontal asymptote on the x-axis. So when y is 0, we've got kind of like a split in the graph. Excuse me, so we've got a split vertically. We've also have a split horizontally, and that's a horizontal asymptote. So these boomerang shapes have to fit in this grid. So these asymptotes make a grid, and this piece has to fit in the top right of the grid, which is our first quadrant, and this one has to fit in the bottom left, which happens to correspond to the third quadrant. So when you guys graph these and you want to do transformations with the rational functions, these would be your key points. 1, 1, -1, -1, and then the asymptotes. So the asymptotes are like your other key points, super important features of the graph. So when we list the domain here, if we list this in set notation, so we want the set of x's such that x does not equal 0. So you can see it from the equation. It would cause the denominator to equal 0 if we put a 0 in for x. And you can see on the graph, you can see that split in the graph at x equals 0. Same thing for our range. We'll have the set of y values such that y does not equal 0. Same thing. If we go bottom to top of this graph, so we go all the way down from -infinity, we're increasing until we get to 0 and we have a split. And the graph picks up just above the split, and then it goes all the way up to +infinity. So it's everything except 0 for the y and the x. Now we can see because of these asymptotes corresponding to the axes, these boundary lines, we will have no intercepts. And we listed our key points, our 1, 1, and our -1, -1. And then again, when you guys do these graphs, those asymptotes will be your other key features of your graph. So we have a horizontal asymptote at y equals 0. We have a vertical asymptote at x equals 0. And we do not have any oblique asymptotes. We'll talk about oblique asymptotes here shortly. Oblique asymptotes are the slanted or tilted asymptotes, and we don't have any of those here. Now the end behavior. If we describe this graph at the ends, so as I trace along my function to the right, as my x gets larger and larger, if you notice it's flattening out, and especially if you guys graph this on the calculator, even in your paper, it's going to start to look like a horizontal line here. So it's going to get closer and closer to 0, but never cross it. So that means as we approach, so we're going to write this as x approaches, remember that arrow means approaches, infinity. So as x gets larger and larger, my f of x, my y value, will approach 0. Now on the other end, as I trace to the left, infinitely to the left, so x is getting smaller and smaller and smaller, we can see it's flattening out again here, and it will never cross that boundary line, that horizontal asymptote. So then we can say the end behavior at the other end, as x approaches negative infinity, excuse me, f of x also approaches 0. Now, we also want to describe the behavior of this function, of rational functions, around the asymptotes. So specifically this vertical asymptote. So we wanted to describe this behavior. We can see we have a piece of the function on the left of this asymptote, and we have a piece of the function on the right. So if I describe this from the left, so as I trace along this branch or boomerang shape, as x gets closer and closer to 0, we can see this function's getting infinitely smaller. The f of x is approaching negative infinity. So the way we'll indicate that, we'll say as x approaches 0, and I'm going to use a negative superscript, a negative sign, and that's going to indicate as x approaches 0 from the negative side, from the left side. I can say f of x approaches negative infinity. So then I can say, now I'm going to talk about the piece that's to the right of the vertical asymptote. So as I trace along this branch shape, this boomerang shape, as x gets closer and closer to 0 from this side, the y value is getting infinitely larger. So we can say, as x approaches 0 from the right side, and I'll use a positive superscript to indicate that. So 0 plus f of x approaches positive infinity. So if you guys want to make a little note, this 0 negative, the negative superscript, this is describing the behavior from the left of x equal to 0, of that vertical asymptote, and this 0 plus is describing the behavior from the right side, the branch that was to the right of that vertical asymptote. Okay, so now we'll look at the other parent function. Our f of x equals 1 over x squared. So we'll make our axes here. So again, let's try those key points that we like to plug in on our parent functions. -1, 0, and 1 if we can. So if I put in a -1 for x, I'm going to get 1 over -1 squared, which will give us +1. So one of our key points will be -1, 1. Now, if I put in a 0 for my x, I can see this function will become undefined because I'll have a 0 in the denominator. So it turns out there's going to be a vertical asymptote at x equals 0. So those excluded values, values we exclude from the domain, cause vertical asymptotes. And then we'll try plugging in a x value of 1, so 1 over x squared will give us 1. So we have another key point, 1, 1. So now you can see we're actually going to have a branch in the first quadrant and the second quadrant. So the 1 over x graph had a branch in the first and third. Both of these branches are going to be above the x-axis, and you can see that's because x is squared. So we'll never get out a negative y value here, because even if we put a negative x in, it'll square and become positive. So we also have here a horizontal asymptote on the x-axis. So at y equals 0, we have an asymptote. So there's that grid, and we're going to fit a branch in here and here. So I'm going to fit my branch shape within this grid, and I'm going to fit this branch shape in this grid. Now be careful when you guys sketch these. You don't want to do this. You don't want your branch to come back up because you need to show that you understand the behavior. And the behavior is, as this branch gets closer to an x value of 0, it almost becomes vertical. It's approaching that vertical asymptote. And same thing here, as this x value gets smaller, it's actually approaching that x-axis, that horizontal asymptote. So you don't want to show it coming up here or coming away here. So that might be a point or two off on a quiz or a test if you don't show this approaching behavior. So if you guys, when we do transformations of this parent function, we need to show the key points 1, 1, negative 1, 1, and then those asymptotes are the other key features. So if we look at our domain, we have the set of x's such that x cannot equal 0. Again, that's because of that split in the graph, that vertical asymptote. And then we have our range, the set of y's such that y does not equal 0. Again, same reason, we have this split here, and actually in this case both of the branches are above that split, but we want to know that these branches get closer and closer to that horizontal asymptote but never cross it. Now again, because of these asymptotes corresponding to the x and y axes, we know we do not have any intercepts. We listed our key points, negative 1, 1, and 1, 1. We have a horizontal asymptote at y equals 0. We have a vertical asymptote at x equals 0. And again, we don't have any oblique asymptote, no slanted or tilted asymptote. So now this end behavior. Let's look at the graph as x approaches infinity. So as we trace along the right side of our graph, as x gets larger and larger and larger, we can see the graphs flattening out. Oh, whoops, I hit the eraser here, sorry. As x gets larger and larger, we trace along this branch. The y value, it's getting closer and closer to 0, but never crossing. So we can say as x approaches infinity, f of x approaches 0. And now if we look at the other end, as x approaches negative infinity, so if I trace along the left branch, as x gets smaller and smaller and smaller, the graph again, it's flattening out, approaching a y value of 0. So f of x approaches 0 here as well. And then if I look at the behavior around the vertical asymptote, so if I look from the left, I have a branch to the left. As this branch approaches an x value of 0, as x gets closer and closer to 0, we can see that the y value is increasing infinitely. So we can say, as x approaches 0 from the left side, f of x approaches infinity. Oops, sorry. And then if we trace along the right branch, so as we trace and approach a 0 from the right side of that vertical asymptote, same thing is happening. That y value is getting infinitely larger. So we can say, as x approaches 0 from the right side, which we indicate with that plus sign, 0 plus, f of x is also approaching infinity.